Hello everyone, welcome to this video. Today I'm gonna show you how to use the FFT functionality on LTspice for your Lab 3 simulations. So you're already familiar with this schema. We have a simple voltage source grounded, so we're able to provide a voltage at this terminal. You can, if you want, as the example that Alex sent on Canvas, you can add a resistor in series. That's completely fine, but for the purpose of this video, we can simply do this. So we're going to start with the simplest exercise. We're going to have just a sine wave of amplitude, let's say 10 volts, and a frequency of 60 hertz. Okay, and we're going to simulate this. So in order to do that, we need to add the directive of dot transient simulation from 0 to, let's say, 0.5 seconds. That it's going to be our simulation. We run the simulation and then we can click here on this node, and we're going to be showing the voltage that it's being provided. Of course, this voltage has a unique frequency related to it. So we want to see this now in the frequency domain. To do that, we're going to right click here. We're going to go to View, FFT, and then we're going to select either voltage or current. This is an open circuit, so current is going to be 0. We don't care about it. Voltage, and we get the FFT. Now the FFT by default, it's defined in dVs, which is not very useful for practical purposes. So what we're going to do is we're going to go to the y-axis, right click, and we're going to change this to a linear scale. So what it does, it's those minus 120 dB, which is a very, very, very small value. It's going to get basically confused with 0, which is what we want. In this case, we only have one main frequency, which is at 60 hertz. In fact, you can add the grid, you can add data points, and you can see that this one is actually almost 7, a little over 7 volts, which is 10 divided by the square root of 2. So the FFT by default is in RMS values, and no harmonics are present on this signal, which is what we expect, right? It's a pure sinusoidal wave. That should be clear. Now let's go to a more complicated example. Now, instead of using one of these default signals, we're going to use a file to account for other types of signals, like a triangular wave or a square wave. On the PWL file, then we're going to select or browse the folder that we uploaded on Canvas, where we have especially the square wave. Okay, we're going to go here. So if you see the path, it says square wave of 60 hertz, 1.5 seconds. That means that the period of simulation considered when we created this signal was 1.5 seconds. Still, we can do less than that. We're going to keep our 1.5. So the difference is now is that we're not defining this function. It's being defined by this file. So we can still run the simulation, measure this voltage, and here it is, our square wave as expected, right? If you zoom in, you can see that it is actually a square wave. And now we would like to know what is the FFT of this signal. So right click, same steps, FFT of this voltage, perfect. And then we get this function. Again, it's kind of odd because it's in the dV scale, and of course everything that it's below minus 40 dBs is basically zero compared with these peaks that are close to 0 dB. So right click on the y-axis, we make it linear, and then we see that there is a, in this case it's a 1 volt amplitude, maximum amplitude square wave, so it's almost 1 for the fundamental, and we have plenty of harmonics, which are multiples of the, in this case, are multiple of the fundamental. So this is, actually, let's do that. Right click, data points. This one is 60 hertz. This one is going to be 3 times that, so 180. This one is going to be 6 times, and so on. So there are multiples of the fundamental, and the amplitude has a relationship also, but that doesn't matter for this case. You're going to study that on a power electronics class. For now, you need to identify what is the magnitude of this fundamental and the magnitude and frequency of the harmonics related to the signal. I hope it helps. Thank you.